Okay, so gentlemen, I just really quickly wanted to go over a couple things about solids and liquids. Uh, and you should know the properties of gases already. Mostly, just remember that this is a competition between intermolecular forces, which want to hold everything together, and kinetic energy, which is basically temperature, which wants to pull everything apart. The faster something's going, the less force intermolecular forces have, the less impact they have. So the stronger the intermolecular forces, the more something stays solid and then liquid and then gas. In other words, the more temperature you have to put in to make it into a liquid or a gas because it's being held together really tightly. And the opposite is true as well. The other thing to know is that pressure is another way to slow particles down. So even if something doesn't have that much intermolecular force and it's at a relatively high temperature, if you put enough pressure on it, it will eventually be forced to slow down because of all the pressure pushing it together. And you can condense things back into a liquid that way, even though under regular pressure they would be a gas. But if you condense them enough, they can actually become a liquid. So I'm going to briefly talk about what evaporation and boiling are, and then I'm going to talk about the vapor curve, which isn't too complex, but I just want to make sure everyone knows what they're doing. So this will be maybe 4 or 5 minutes, and that should be it. Okay, so I'm just going to talk real quick about a couple things. First of all, I want to talk about just the definitions. So boiling and evaporation are both types of the phase change known as vaporization. So vaporization is anytime a liquid converts into a gas. There are two types, evaporation and boiling. Evaporation happens below boiling point, and it's when a few particles have enough kinetic energy that they're able to escape from the surface, from the intermolecular forces, hit the surface and kind of escape and turn into a gas. And boiling is when you heat a liquid to the point where all the particles in the liquid, regardless of whether they're on the surface or in the middle, have enough energy, kinetic energy, to vaporize. In other words, to turn into gas. So evaporation can only happen at the surface of a liquid, and boiling can happen throughout, which is why you see bubbles when water boils. That's not air entering the water, that's just water turning to gas, and the gas water makes bubbles in the liquid water. So really quickly about evaporation, I've got this awesome professionally drawn chart up here. So one thing you have to know, we haven't really talked about this, temperature is a measure of kinetic energy, how fast particles are going, and we've talked about that. But particles at a certain temperature, if we measure a sample of water and it's, let's say, I don't know, 20 degrees Celsius, little under room temperature, close to room temperature. Well, that doesn't mean every water particle has the exact same kinetic energy and is going the exact same speed. It's an average. So what the thermometer reads is an average. And the average generally sorts out kind of like a bell curve, like I've drawn here. So number of particles on the bottom and kinetic energy. And you see most of them kind of clumped at any given temperature, most of them clump together in a fairly narrow range. And there's a few on either extremes. And what happens is the ones that are most likely to evaporate are the ones at this high end of kinetic energy. They have the most kinetic energy. They're the most likely to hit the surface with enough energy to escape the liquid. The interesting thing about that is when they evaporate, what they leave behind is water with a lower average. So if I take the highest average students away from the class, so I take the top highest, 5 highest average students away from a class, that class average goes down. Well, if you take the highest kinetic energy average away from the liquid's kinetic energy average goes down. In other words, its temperature goes down. So evaporation is a cooling process because what's left behind actually has a colder temperature because the hottest particles, you want to think of it that way, the most kinetically, the highest kinetic energy particles went away. So that's why we sweat, to cool ourselves, because evaporation is a cooling process. So that's why sweating works. The other thing I want to talk about quickly is the term dynamic equilibrium, because that kind of sounds like a complicated term, but this is actually something you've seen. So if you have an open bottle of water, that water will eventually all just evaporate. All the particles will eventually get enough, assuming it's at like room temperature, will get enough energy to escape the surface of the liquid, and as it takes in more energy, they'll get more ability to escape the surface of the liquid, and they'll just hit the opening in the bottle and go out into the greater atmosphere. But if you close that system, in other words, if you cap the bottle, what happens is particles will start evaporating, but as they evaporate, they're adding to the gas. So this gas phase has more and more particles, and they're stuck in the same space, so there's a greater pressure. So you keep, excuse me, you keep pushing up more pressure in the gas, and eventually that pressure maxes out the amount of water that can be in the liquid phase, or in the, excuse me, in the gas phase. So any given sample of gas can only hold so much water. That's what humidity is. It's how much percent of the total water the air can hold that it's holding. So when it's 90% humidity outside, that doesn't mean 90% of the air is water. That would make it very hard to breathe. That would mean that the air is basically holding 90% of its capacity of that temperature. Not a lot of the total percentage of air, but 90% of all it can hold. So as pressure goes up, the amount of energy it takes to evaporate goes up because you have more and more pushing down. So for water to escape, it now has to escape to something that's pushing down harder on it. So eventually you get to this point of dynamic equilibrium, where every time a water molecule evaporates, another one has to condense back into liquid to make room for it. Because the water molecules aren't smart. They don't know, oh, it's filled up there. I can't evaporate. It just happens to push another one back into the liquid. And if you've ever seen a water bottle that's been left out, you actually see this because the liquid doesn't have to condense back at the bottom. It can condense on the sides or the top. So you leave a water bottle out, what you'll see is, if it's half filled, eventually you'll get a bunch of droplets at the top and on the sides of the water bottle because some water evaporated and then had to condense, and it will condense on the sides and the top as well as back into the liquid. So that is dynamic equilibrium. Dynamic equilibrium does not mean that there are the same amount of water particles as liquid particles. It's not a 50-50 split. It just means that the ratio is staying the same. So if there are 99 water particles, liquid water particles, for every one gas water particle, that ratio stays the same, even though the particles are switching places. Because for every particle that evaporates, one condenses. That's what a dynamic equilibrium is. It means the overall ratio is staying the same, and the particles are switching places. It does not mean you have an equal number of one thing as another. It could be a 50-50 ratio. That'd be kind of rare. But it just means it's not changing even though particles are condensing and evaporating. They're doing so at an equal rate, so nothing changes. Okay. So, really quickly, what is boiling? So, boiling is just when you've raised the temperature of a liquid enough that its vapor pressure, the pressure pushing off of it because of all of its vaporizing particles, equals external pressure. So when vapor pressure equals external pressure, usually that's atmospheric pressure, that's boiling, and you'll see it as boiling. That means you can boil water one of two ways. You can either heat it up so that its vapor pressure equals external pressure, that happens at 100 degrees Celsius, or you can take pressure off of it. You can put water into a vacuum chamber and remove pressure, and you can remove pressure to the point where it will boil at room temperature. This was something I was going to do in the class, and maybe I'll go in and do a video of it. But it's not hot; it's just boiling because it has no pressure on it. So its vapor pressure at 20 degrees Celsius is enough to make it boil. So there are two components to boiling: vapor pressure equaling external pressure. So temperature and pressure both determine boiling. Normal boiling point is what we think of when we think of boiling point. We say the term normal boiling point in chemistry is mean boiling point at regular atmospheric pressure. Okay, so one last thing I wanted to look at really quickly. Let me bring up the key to the homework. Okay, I just wanted to talk about how to read this vapor pressure curve really quickly. So on the x-axis we have temperature, on the y-axis we have pressure. And then we have three chemicals: diethyl ether, ethyl alcohol, also known as ethanol, and water. And all it's showing you is as you raise the temperature, you have a greater vapor pressure. In other words, as you raise the temperature, particles are evaporating faster, so you have more pressure above the liquid because there's more gas particles there. So, 760 millimeters of mercury is standard atmospheric pressure. So when vapor pressure equals external pressure, that's boiling. And so you can follow these lines and see what temperature that happens at for each of these chemicals. So for diethyl ether, you'll notice it's 34.6, which is right there. That's the temperature when it crosses this line, the 760 millimeter mercury line. For ethyl alcohol, that happens just below 80 degrees Celsius. And for water, it happens at 100 degrees Celsius. So that's where it's the temperature where it's vapor pressure equals external pressure. If you wanted to find out, let's say we drop the external pressure to, the question asks, I believe, 400 degrees Celsius, or 400 millimeters of mercury, not 400 degrees Celsius. You would just read it and see where each of them crossed 400 degrees Celsius. So 400 millimeters of mercury, excuse me. So you just take 400 millimeters of mercury and kind of extend that line over and say, okay, diethyl ethyl crosses it about here at this temperature. Ethyl alcohol crosses it about this temperature. Water crosses it at about this temperature. And that's how you'd find the boiling points of those things at different pressures. But at standard pressure, it's this line right here. Standard, so the normal boiling point at standard pressure is this line right here. I'm not going to talk much about solids. They're pretty straightforward, and we're not going to use anything with them much in the future. So I just wanted you to watch that video and kind of get a background. I will put a key to the liquids and gases worksheet up. The solids worksheet, just, watch the video, do the key. If you have any questions, email me or ask me during the Zoom meeting. Okay, have a good day.